Bismillahirrahmanirrahim. Let us see how the bolts in shear theory works in practice. This is a problem where a bracket in blue is attached to a pillar in gray using 3 bolts. We are supposed to find out the factors of safety for shear of bolts, bearing of bracket, and the bending of bracket. This last one, bending of bracket, is not directly concerned with bolt design as such, but we'll just take a look at it. As far as the bearing of bolts is concerned, as discussed earlier, whenever a joint fails as a result of bearing stress, most probably it is the member that fails, not the bolt, because the bolt is usually made of a much stronger material. But we'll take a look at the bearing of bolts as well. Now this 12 kilonewton load is obviously an eccentric load, and we need to shift it to the centroid of the bolt group, and that centroid happens to be this point, very obvious. Now if this is shifted here, this shifting also entails a moment couple M. This is basic statics, and the value of M will be simply 12 kilonewtons multiplied by this moment arm 200, and so the value of M turns out to be 2400 kilonewton meters. Millimeters. 2400 kilonewton millimeters. Now we are going to treat this 12 kilonewton load and this 2400 kilonewton millimeter moment separately. One will cause primary shear and this other will cause a secondary shear, as discussed in the theory. Now as far as the primary shear is concerned, let us name this bolt as bolt number 1, bolt number 2, and this is the bolt number 3. So the primary shear F1 prime, which will be equal to and also equal to F3 prime, these are all equal because all the bolts share this load equally. This turns out to be simply 12 kilonewtons divided by 3 because there are 3 volts and you have 4 kilonewton. This is the value of the primary shear. As far as the secondary shear is concerned, here we have to employ the expression that we derived in the last class, and this is simply F1 double prime will be equal to MR1 over R1 square plus R2 square plus R3 square, where the distances R1, R2 and R3 are distances from the centroid of the bolt group to the center of each bolt. So M1, the distance will be, R1 distance will be 32. The value of M, 2400. Note that R2 is 0. Second bolt lies exactly at the centroid of the bolt groups. And this turns out to be 37.5 kilonewtons. Now F2, this will obviously turn out to be 0 because we just mentioned R2 is 0. F3 double prime will be exactly equal to F1 double prime because again the distance from bolt 3 to the centroid of the bolt groups for both bolt 1 and bolt 3. They are the same. So you just simply write it down as 37.5. The directions will be different, obviously, but as far as the magnitudes are concerned, they are the same. We'll have more to say about the directions. Now it is obvious that the primary shear values are equal for all. So the bolt F1 and F3 will govern the design because F2 double prime is 0. So we need to design on the basis of bolt 1 or bolt 3. Same thing. The direction of F1 and F3 primes are simple enough. This is F1 prime. This is F3 prime. These are the same directions as the applied load. As far as the directions of F1 double prime and F3 double prime are concerned, please recall from the theory that it is simply a matter of joining with the help of a straight line the center of the bolt group with the center of the bolt in question, and the shear will be perpendicular to that line. Now considering that the bending moment is clockwise, therefore the F1 double prime will be at 90 degree to this line that joins the centroid of the bolt group to the center of bolt 1. Similarly, if we join centroid of the bolt group with the center of the third bolt, and considering the direction of M, which is clockwise, F3 double prime will be again perpendicular but in the opposite direction. This is perpendicular. The resultant of F1 single prime and F1 double prime and F3 single prime and F3 double prime will be the same. So it doesn't matter. So we can simply take any one of them and we need to find out the resultant of the two. Because F1 prime and F1 double prime are perpendicular to each other, the resultant F is simply F1 prime square plus F2 plus F1 double prime square under root. If F1 prime and F1 double prime were at any other angle except 90 degree, we would then have used some sort of graphical addition or sine law or cosine law. In this case, it is simple enough. It is simply 4 square plus 37.5 square under root, and so thus it turns out to be 37.7 kilonewtons. This is the load on the most critically loaded bolt of the system, which happens to be bolt 1 and bolt 3 as well, because both are subjected to the same shear force, only the directions are different. Now we take up the first part of this question, shear of bolts. Let us first calculate the shear stress. Tau is simply shear force that we just calculated, this 37.7 divided by the area of shear. Now this area can simply be calculated by using the nominal bolt size, because the problem statement says that the bolt threads do not extend into the joint. So it means that the plane at which the bolt shears is the shank part of the bolt, not the threaded part. So it is simply a matter of, in this case, it will be 5/4 12 square. And this means that the shear stress turns out to be 33. Obviously, we have to convert this into newtons. Now, the shear stress comes out to be 333.33 megapascals. This is the stress on each bolt. Now, what about the strength? From table 811, against ISO 5.8 class of bolts, SY is, the yield strength is 420 megapascals. Now, this is obviously the yield strength of the material. This is not the yield strength in shear. If we use the maximum shear stress theory or the Tresca theory, then we simply multiply this by 0.5 to get the shear strength, to get the yield strength in shear. 0.5 into 420, which is 210 megapascals. If we use the distortion energy theory or the von Mises theory, then we get a slightly higher number for the yield strength in shear, and that number is 0.577 into 420. This turns out to be 242.5 megapascals. In this analysis, we'll just take the conservative value. So if we, using this value, factor of safety in shear turn out to be SSY, yield strength in shear, divided by the shear stress. And this is 210 over 333.3. This turns out to be 0.63, which is obviously not good enough. Right? The bolt fails in shear. Now we come to the second part, which is the bearing of bolts. Bearing stress will be force, which is, in this case, we know it is 37.7 divided by the bearing area. Now the bearing area is simply the projected area. The projected area, which means it is T into D. T is the thickness of the plate, and D is the nominal diameter of the bolt. The threads do not extend into the joint, so we don't need to worry about the threads. All we need to do is simply calculate the projected area. 8 is the thickness of the plate and 12 is the nominal diameter of the bolt, and this turns out to be 392.7 megapascal. Recall that bearing stress is always compressive, so the minus sign will always go with it. And then the factor of safety for the bolt is, now let me specify it by using bearing of bolt. In this case, the yield strength we just found out will be 420. We are not going to halve this in this time because we are not concerned with the shear yield strength in shear now. We are concerned with the yield strength, compressive stress being a normal stress. And this turns out to be 1.07. This is barely okay, but I think it is obvious that if the bolt is so close to failing, although it hasn't failed, the member is most certainly going to fail. Let us see. For the bearing of members, sigma b is the same. The only difference is that the member strength now is different. Member is made up of AISI 1020HR hot rolled and from table A20 we can see that the yield strength for the member is 210 megapascals. Now using again the same formula, this time for bearing of members, we have SY in this case will be 210 divided by 392.7. This means that this turns out to be 0.53. Again, this has failed. Now we come to the bending of bracket part. It is obvious that this bracket is a cantilever beam and the bending moment of 2400 kilonewton millimeter causes the maximum stress on the plane shown in yellow, and the maximum stress on this plane will be on the two extremes. Maximum tensile stress will be here. So using the bending theory, sigma will simply be my over I. We know the value of m is 2400. The y value will be the distance from the neutral axis to this point, which happens to be 68 millimeter. So we know this. The only thing that we need to specially consider here is the calculation of the second moment of area I, because on this section of interest there are 3 holes, so we need to cater for these holes. Let's do that. So when it comes to the bending of the bracket, the situation is something like this. We have this bracket. I'm going to draw the cross section of the bracket at the section of interest. That happens to be the section where there are the bolts, the 3 bolts. Now we have 3 holes there. The thickness of the bracket is 8 millimeter. We know that. And the distance from the neutral axis to the point of the maximum stress is 68 millimeter. We also know that. All these holes are 12 millimeter each, and the height, total height, again given in the problem statement, is 136 millimeter. It's a cross sectional area, so let me put some etching on it. We need to calculate I for this. Recall that ultimately we are going to use sigma my over I. M is known, y is known. The only unknown here is I. Let us calculate I here. We are going, it's a rectangular shape, so BD cube over 12 is the formula for the second moment of area. In this case, 8 into 136 cube over 12. But this gives us the second moment of area for the whole section without the holes, without the bolt holes. Now we need to cater for the 3 holes. First of all, taking the center hole, this one, we subtract 8 into 12 cube over 12. It's simple enough. But when it comes to the other 2 holes, this one and this one, because their centers are displaced from the centroid of the whole figure, centroid of the whole structure, therefore we need to use the parallel axis theorem. So taking the upper hole, we will have to subtract 8 into 12, but we need to employ the parallel axis theorem, and the parallel axis theorem is simply a into d square. This the area of the hole is 12 into 8, and the d happens to be the distance of the center of this area to the centroid of the whole structure. This happens to be 32. 32 square. And because hole 1 and hole 3 at the bottom, they are exactly symmetric, we can just put a 2 here. So this gives us a value of 1.477 into 10 raised to power 6 millimeter power 4. This is I. Sigma then turns out to be M, we know 2400, but it is kilonewton. We convert it into, and we have so the stress turns out to be, in this case, 110.5 megapascals, and the factor of safety for bending comes out to be SY over sigma, and this SY we just found out for the plate 210, sigma 110.5, and so this implies that M is equal to 1.9, which is again okay. A quick recap: the bolt has failed in shear and the member has failed in bearing, and this need not be a cause of worry because design is an iterative process. So the next iteration should be based on the following. To safeguard the bolt shear, a bigger size bolt can be used, or a bolt of a stronger grade. As far as the bearing failure of the member is concerned, that can be prevented by use of a plate of a larger thickness or material of a higher strength, and of course bolt of a bigger size will also help.